check yourself.
Okay, so today we're going to start talking about the memory system, which ends up being one of the most important topics, and by pretty much the most important topic inside of architecture. If you get nothing else, please understand how memory system and caches work. For both, for cybersecurity, caches is going to make sense at the end because it's what enabled Meltdown and Spectre to happen, and we'll hopefully get to that. But more importantly, from architecture standpoint, why do we have caches? Well, it's based on performance. And I've debated on the best way to introduce caches. So usually I give a lecture, a theory, and then actually show practice. This time, let's just go straight to an example about why it's so important and then see if that helps you understand what's going on.
Probably not.
Probably not at all? All right, so let's go to an example. Has anyone completed linear algebra? All right. So what's matrix multiplication?
Not fun.
I don't remember.
You multiply two matrices.
Good job. Wow.
You did? Okay, great.
That's the answer. You multiply two matrices.
I mean, yes.
You just asked what it was. You didn't ask how to do it.
Touche.
So, you have A1, A2, A3.
It's going to be lovely to see on the board.
Wait, we're going to do A11. Let's do it this way. Can you not see it? Oh, it's nice and tiny. Good.
Yeah. No dying.
And I'm only starting at 1 because that's how math people do it. Yeah. Otherwise, it'd start at 0. When we go to code, it'll definitely be starting at 0 because, yeah, this is kind of silliness.
Oh, dang it.
What?
I'm just looking at stuff. I was trying to figure out if operating systems and algorithms are online.
Oh, yeah, we're registering.
Oh, no, there's
economy.
Okay, so how do we get this one?
Multiply.
Magic.
Is it A11 and B11 and A11? Dang it. Ashley, gotta come on this side.
No, you're good, Ashley. You got to represent. Now that side of the class fully loaded. This side over here.
Is it something like you multiply it by, so it's the, God, is it like the first column and row or something, or?
Yeah, you had to like add a row together or something and multiply. It's been a while.
All right, anyone in linear algebra right now?
Yeah, you like multiply like.
Come on, you just did this.
It's like.
Okay, so what's the first thing? It's A11 times B11, right?
Yeah.
Yeah, so we got A11. Oh, that's a lot better.
You're not gonna be able to see that at all. Please tell me sound is working.
Oh, sound is totally working. All right, but that's not the end of it. What do you add?
A11
times B12. I think.
Oh wait, no, is it row?
No, it goes
column?
like row to column.
Yeah, so
Okay, so A11 times B21.
That'd be A12 times B21.
yeah, I think that's. I keep forgetting too, because remember
Right.
you got to go. You start here and then you, what was it, row column? So boom,
Yeah.
boom,
Yeah.
right?
That's so weird.
It is weird, isn't it? Well, anyways.
Now we use our calculator for this. We don't have to do it now.
By hand.
Test 1 was by hand.
And then you also add, I think it's A13 times B31. All right, so a bunch of row columns, and you have to do that for each one of them. Okay, let's go code this up real quick.
Just real quick.
Well, what else would you do? Slowly? Who wants to do it slowly?
If you do it at my speed, we won't be done till like a month from now.
All right, so let's go ahead. Oh, let's G-Vim this.
Why have you changed
What?
from Vim to GVim?
Because I had people complain that the black background is too hard to see.
No.
Do you like the black? Okay. Everyone okay with the black background?
Yeah.
All right, good. And we are using it because otherwise you're
It's
just
actually
lame.
better for your eyes too.
Oh, I completely agree.
I figured out how to change the color scheme.
All right.
Yeah, because it was really hard to see, like, for our presentations and stuff, how we couldn't see your things. I figured out how to change it.
All right, so let's create a size for this. We'll go ahead. Actually, we're going to call it width. Define width. I don't know. How big do we want it? We'll start with something simple. Wait, what is that? Does anyone know what what does that mean? So we have our bits.
21 and 6.
This is great. All right, so we're taking the value 1. I don't know why I drew a 0 there, but you know, just roll with it. There's a 1. You know, I took out the nice marker for this. And we're going to upshift it by 6. That means we're going to take the 1 and we're going to shift it up 6 times. So 1, 2, 3, 4, 5, 6. So now it's 1. Now what's the value? It was 1. Now it's
1 million. Oh wait, binary.
no. This is binary.
1 million.
1 million. 1, 2, 4, 8, 16, 32,
64.
64. What did we really just do?
Get another person on our side.
Good morning.
Good morning.
If you take 1, you upshift it by 6, you're really just computing 2 to the 6th. Because each time you shift, you're multiplying by 2. Now, is this a complex operation or a simple operation? Simple. So this is actually really, it's not going to be multiplication where you have to go through all these weird stages. It happens very quickly. All right. So let's go ahead and define some matrices, because we like matrices.
Sure.
Yes.
Yes.
Been a while.
And we'll go ahead and create B, and we'll create C. All right, great. Now we need to go and fill them up with something. So let's get some random numbers. I like comments, even if they're heckling.
No, I asked Matt, I said, wait, are we going back to C++? Because we've been MIPS. And he said, no, it's C.
No. We're not. Objects are crazy. That's way too complex for this class. We're not even going to go there. All right, so A sub I sub j equals, what are we going to do? We're going to convert to a double rand, and then we'll divide it by rand max. Perfect. We'll do the same thing for B, and then we'll make sure that C starts at 0. All right, and let's just make sure that we are getting some random numbers. We'll just copy this down. %f, a sub I sub j, and then we'll go ahead and give it a /n. All right, let's go and compile that. GCC. We'll turn on optimizations.
Oh, GCC, I remember that.
Well,
Okay. All right. Yeah. So it printed out a bunch of random numbers. So we are getting random numbers. Looks like they're going between 0 and 1, which is good because they're doubles. So we're getting something random. All right.
Fun.
So that's good. Let's go ahead and just let's make this simpler, and let's just print off 10 by 10. Let's see if that fits on the screen. Oh, okay, there. So we're just printing out some of the numbers just to make sure some of these work. Okay, great. Let's go ahead and create our little function called matrix multiplication. Matrix multiply. And I'm lazy, and I'm going to make everything global, which is usually bad programming practice, but I don't care right now.
Oh, awesome.
All right.
Can we do that for our lab?
No. You want me to do it correctly?
Yes.
Oh, okay.
It's for our lab.
This isn't for your lab. This is just messing
We're not
around.
making it lab.
No. So, matrix multiplication.
Yes.
We need to go from what to width, I++. We have to do the same thing for j. All right. So how do we compute c sub I? Well, we need to go through.
Each thing.
Right. So we actually need to go through how many things?
N.
N. Mhm. So we need another for loop.
Yes.
So C sub I sub j plus equals, I always forget this, A sub I sub k, because that's
How
the,
much we use this.
this is because it's the row, times B sub k sub j, because it's the column. And then that's it. Right? You just do that for every element, we call it a day. So let's go up here and let's see what C looks like when we're done. Make sure we're doing something that makes sense. Hey, a bunch of zeros, so we're not doing it. You know why?
Because we didn't call it.
Oh, we didn't call it. Nice. Doing all the work and then not actually telling the computer to call it. Classic. Okay, that looks all right. All right, numbers. Okay, so
And they're bigger.
with computer architecture, what do we care about most of the time? Security is actually secondary. Sorry. But what do we actually care
Does
about?
it work?
Does it work? And then,
Does it run?
does it, well, yes, which we got. And then lastly,
Is it efficient?
is it efficient? We care a lot about performance a
I
lot.
guess.
So let's go and get some timing numbers real quick.
It's probably very simple.
Since you have 3 for loops, would that be a big O in cubed?
Yep, it's O of n cubed.
Sadness.
So let's go. Start equals clock, and then end equals clock. Now we haven't gone to operating systems. There's a couple of problems doing it this way, but it gives us a good estimate of what's going on. All right, so we'll have diff equal to end minus start. And then we'll print that off, and then down here we'll go print f, %f. We'll say took time, %f seconds. And I think that's diff minus clocks per second. Uh-oh. It's not highlighting. Oh, it's because that needs an S. Whew. So what this is doing, the clock gives me the number of clock cycles that happened here. Run the function, give me the number of clock cycles. Diff, subtract the two. Down here, take whatever the diff is, divide it by clocks per second. How many clocks tick per second, defined by our computer. And that should hopefully give us the amount of time at the end. All right, let's go ahead and run this. Hey, 0.0307 seconds, so it's pretty fast. Let's see if we can slow this down a little, which is real easy because we just increased this number. 0.04, okay, let's make it a little slower.
About like 20.
Well, hold on, let's go with 9. Oh, 9 took half a second.
Ooh.
Now let's go ahead and run it again. Let's do it one more time. Usually we want to do it about 3 times. All right, we'll say it takes about this much. That's good. And then let's go ahead and do it at 10. Bum, 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 ba, bum, ba, 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 bum, bum,
Why are you singing that song?
I don't know. Just when I was working and something took a while, I had a coworker, he always had it ready. Once something started taking more than about 2 or 3 seconds, he just started playing it.
Oh, there you go.
14.7 seconds, okay. All right.
Yeah.
Wow, we're complaining about 14.
Yeah, I know.
Okay, so, all right, let's go ahead and put this back down to something a little more reasonable. Let's say 7. It runs. Okay, actually, let's do 8. How long is 8? 8's still pretty good. Okay, so, all right, everyone following me so far? Because I'm about ready to do something that's going to appear completely random. Nothing, anyone confused. This should all be pretty somewhat straightforward. I wrote a program, I did some timings, things are good.
Yeah.
All right.
Now you're gonna break it.
No, I'm not going to break it, I'm just going to change it. Instead of regular matrix multiply, I'm going to matrix multiply blocking.
A more efficient way.
Maybe. Hopefully. We'll see. blocking. All right. Ignore the word blocking for now. I'm going to define, we'll call it a step variable. 1 upshifted by 4. And what I'm going to do is I'm going to add another for loop. Int ii equals 0. ii is less than width. ii plus equals step. All right, and that by itself would mess up our numbers, right? They wouldn't be correct. But because what I want to do is I want to have I basically run and only run within my certain steps. So I want to start at here ii, and it's going to be going up to ii plus step. All right.
That's not a good sign.
So, am I still going to get the same answer? Question mark? Well, let's see for a moment. Right now I'm running the regular matrix multiply, not the new one I wrote. So we get 66.5388. All right, let's see if we take this and run our new one. Do I get the same answer? Yeah, because all that's happening here is for I only go so far and then run the rest of the algorithm. Then I jump over, run I. Whoops, I'm not recording the video. Well, actually I is going this way. So I only go I so far, do the whole calculations, jump to the next step, only do it within that block, jump to the next step in that block. Okay? Y'all see what I'm doing? It's still going to be the same answers. I'm not just running through it. I'm just doing it in chunks. All right. Well, we're doing it with I. We probably should do that with J as well. So let's do it for J. All right, then we're going to need another closing curly bracket. That's great. Let's run it. And do we get the same numbers?
No.
So we got a problem here. One iteration invokes undefined behavior. Did I miss something?
JJ plus width.
Oh yeah, that's bad.
Yeah, I saw that.
No one stopped me? Wow. All right, so those look like the previous numbers. Let's go ahead and just check that because we've had some things jump around. Okay. Yeah, all right. Let's do it again for K. All right. See, I haven't changed what we're adding. I'm just changing the order we added in, which is okay because addition's associative, right? So that's why we're still getting the same numbers. We'll go ahead and run our other matrix multiply real fast. Okay, there we go. All right. Numbers are still the same. Let's do a quick evaluation. Whoops. Let me just jump around a lot. So which one of these algorithms, when you inspect it, should run faster?
Blocking.
Why?
Because you're not having to iterate through the entire thing every time, right? You just do
No,
it.
we still iterate.
Well,
through
yeah,
the-
but like in chunks, right?
Yeah, you do it in
You
chunks.
each step in chunks.
Yeah.
Over just doing it all at once, I guess.
Right.
That's why it's faster.
That's why it's. But why is that faster? I don't know. Well, which one's doing more work? Ooh, that's the question. Which one is doing more work?
The first one.
Which one's doing more additions?
Matrix multiply.
Hold on. Oh, no. I'm still. This is still being run the same number of times. C sub I. This, I'm doing that number of multiplication, that number of additions here and here. This line is being executed the same number of times. I'm talking about this line right here. I haven't trimmed off anything. It's executing the same number. Oh, good. We get to have a little bridge run that day. All right, we could see what happens. So but I have these 3 extra for loops, which means I'm adding more additions, and I'm adding more comparisons as well, and I'm adding more variables, which means I'm using more registers that the compiler can't use to optimize this. I wonder if I can cancel this. 1 second. Perfect.
They're not sure if there's traffic.
I know. So the blocking is doing more work. Everyone, do you all see what I'm trying to get at here?
Yeah.
Blocking's doing more work. The top one's doing less work. So if the bottom's doing more work, it should run slower because it's
However.
doing more work.
I feel there's a however.
Oh yeah, there's a however coming. So let's go see if that's the case.
No.
We'll see. Define on their previous one upshifted by 9 took half a second. Let's go ahead and run it here.
At the bottom.
Yeah, so
1.8.
0.18. Well, you know what? We have a parameter here, right? We have a step. I wonder if changing the step does anything. Oh, it made it better. 0.19. Okay. So there's some jitter going on here. We'll say it's 0.19 just for sake of argument. That sounds great. Okay, that's definitely faster. Let's try 10. Let's see what happens at 10.
Those are bad.
Those are bad numbers? Why?
It's
Well-
1 second. Well, still not as bad as the 14 second.
Okay. What happened?
Cut the time down significantly.
Right.
It's
Did I change the big O?
Yeah.
No.
No.
You didn't.
No, I didn't. I didn't change the big O at all. We still have 3 for loops essentially in both. It's still O of n cubed. I didn't change the for loop. I changed when we were doing the. All I changed, actually, I just changed when we're doing certain additions and multiplications inside the order. Y'all must be really tired.
Yeah.
The idea, like if you made these huge matrices, what's happening is I'm doing this block times this small block into these blocks over here, and then I move on to another block and do the same thing, as opposed to going all the way across and down each time. The reason for that, as we'll go into, well, the reason for that is one word, caches, and you'll basically for the next, I don't know, 3 or 4 weeks, that's the answer to everything. Caches. Yeah.
Got it.
It's like when you're going through confirmation, they, you know, if you don't know the answer, you just say, Jesus.
Yeah.
Just say Jesus. Here, it's going to be pretty much caching. But before I go on, one last thing I want to point out is, if you were to write matrix multiply, which of these 2 algorithms would you have done?
I would have done the first one.
First one.
First one. What does that imply about most of your code?
Very slow.
It is not optimized. But to optimize it, what do you have to do?
Think differently.
Sure. Apple, I guess. You have to think differently. There's a, you have to start doing some weird things, weird, wacky things to make it happen. And all I'm trying to push to you is that due to how architecture works, some of the things you do are not intuitive. Like you would not intuitively want to do this, right? There's no reason to do this. I would never want to write 3 extra for loops on top of another 3 for loops. No one would want to do that. But it ends up being, in this case, to be faster. And the short answer to that is caching, and that is why we have to study caching for a long time. Yep, which is basically the memory system. So, I'll go ahead and start. Now that I've at least given you an example of what's happening, hopefully the memory system will make a little more sense. We'll revisit matrix multiplication just to show you a couple other tricks with it. Let me go ahead.